Hello, welcome to video 9, where we'll be solving trigonometric equations. Now that we've got trig defined as functions, and we have gone through and evaluated trig at specific angles, what if this has been reversed so that now I know what my trig is equal to, and I want to solve for the angle respective to that trig function. So for example, let's consider sine of x is equal to 1/2. And in words, what this equation is asking me for, and what it's really saying is in this statement in blue. Sine of what angle will give an outcome of 1/2? Right? And there are essentially two different methods to go through and do this. One is understanding again the connection that sine is the y coordinate for an angle on the unit circle. So looking at the unit circle would be my very first method and trying to go through and solve this equation and look for this specific answer. All right, and so I'm just going to go and draw just kind of a basic circle here. I'll draw it in blue. Now let's center this sucker up. Real time, baby. There we go. All right, now when I'm looking for sine is 1/2, I know that because I'm looking at the y coordinate and looking at my y-axis, this would be where y is equal to 1. This would be where y is equal to 1/2. So essentially what I'm saying is if I was to draw a horizontal line at this y value, where would it essentially intersect the unit circle? And these points where it would intersect are associated with the special angles of pi over 4, oh that's wrong, pi over 6 and 5 pi over 6. And if we look at the unit circle specifically, I'll see that at these two angles, that is where I have a y coordinate of specifically 1/2. So one solution for this, or two solutions for this, would be that x is equal to pi over 6 and pi, and x is equal to 5 pi over 6. All right, and here are my two solutions. I could check them by essentially going through and saying sine of pi over 6, but I think it's kind of redundant since we already have the unit circle listed. All right, now the second method essentially comes from graphing it. All right, if I'm looking at this problem, sine of x is equal to 1/2, I essentially have graphically this question. Where does the function sine of x and the function y is equal to 1/2, where do they intersect? And visually, if you are remembering what sine looks like, sine is a wave, which means if I'm going to draw a horizontal line at 1/2, how many times do you think this is actually going to intersect? Let's go through and let's see what you think might happen. All right, so I'm going to pull Desmos up. Let's get my graph in projector mode. Get my x-axis to be in terms of pi. And I'm going to go through, let's type in sine of x. And let's type in y is equal to 1/2. And you'll notice, look how many times this graph intersects. Just in the window that I have right now, there are essentially 2 points of intersection at every crest. So right now I've got 1, 2, 3, 4, 5, 6 different places that these intersect. Now, if I start at 0 and I just kind of zoom in right here, and I'm going to click on these points of intersection. Here is my first solution, which is pi over 6. Here is the second solution that we got before. So see how those kind of work out and how we can find those from the graph. But what the graph reveals that the unit circle does not is that there are more answers. All right, so let's go through and let's list out some of these solutions, and let's only focus on the positive ones. So I have pi over 6 and 5 pi over 6. Well, the next two would be 13 pi over 6 and 17 pi over 6. So I'm going to go back and let's write these out. So from a graph, I have one solution was pi over 6, and one solution was 5 pi over 6. The next pair was 13 pi over 6 and then 17 pi over 6. What about the next pair? All right, so let's go back to Desmos. The next pair was here, 25 pi over 6, and then 29 pi over 6. Let's go back to Notability. So we had 25 pi over 6, and then 29 pi over 6. And this process could continue indefinitely, meaning if I had to count the number of solutions, how many solutions are there to this equation in general? Well, generally, there are an infinite number of solutions, so infinitely many. So if I want to go through and find all solutions, it's actually impossible to go through and find all solutions. The reason being is that I would be here until the end of days listing out just the positive ones, but this doesn't even include negative angles, because if I want everything, I'm also looking at what if x is negative versus when x is positive. So I need a way to represent these solutions. And we actually did this when we were looking at graphing tangent and graphing cosecant and graphing secant, and the way that we wrote the general equations for the vertical asymptotes. If you look at the solutions that I've got listed right now, I put them in columns like this for a specific reason. If you notice, what's the difference between pi over 6 and 13 pi over 6? In other words, what's the change? Well, if you just look at the numerator, notice that this would be a difference of 12 pi over 6. Well, that's 2 pi. Right? What's the change here to here? Look at the numerators again. That changes another 12 pi technically over 6, which is another 2 pi. What does 2 pi represent? Why is this so significant? This represents the period. Right? The graph cycles through every 2 pi. So if I have an answer at pi over 6, that means I'm going to have an answer at every single coterminal angle associated with pi over 6. Well, how do I find coterminals? By adding 2 pi or subtracting 2 pi from this initial solution. So one expression would be x is equal to pi over 6 plus multiples of 2 pi, and that's what this k is counting. K is an integer. So pi over 6 is associated with k is equal to 0, right? If I plug 0 in for k, then this entire plus 2 pi k disappears, and I have just my first solution. If I wanted to do k is equal to 1, find the next solution, the first answer after pi over 6, well, this would tell me to add 2 pi, which is worth 12 pi over 6, and I get 13 pi over 6. If I wanted to get two answers down, I would say k is equal to 2. I would add double 2 pi, which would be worth 24 pi over 6, or another 12 to 13 pi over 6, and get 25 pi over 6. And this process would continue. I would just add another 2 pi, add another 2 pi, add another 2 pi. Well, notice though that pi over 6 is only associated with this column. 5 pi over 6 is associated with every angle below this one, 17, then 29. Notice that this difference is adding 2 pi, etc. Because again, that is how much one full cycle is worth. So I get not only x is equal to pi over 6 plus 2 pi k, but I get x is also equal to 5 pi over 6 plus 2 pi k. This represents both points on the normal unit circle that we saw in my first method, but it also includes every other possible solution, which every solution is worth one period and one cycle away. Now, k being an integer means that it's also including minusing 2 pi, where k is -1, -2, -3, and I'd be doing pi over 6 minus those cycles to get every single negative answer as well. And that's where, if you wanted to test it, notice what this method would say is I would say pi over 6 minus 2 pi. This would be k is equal to -1. I would get pi over 6 minus 12 pi over 6. So this says one other answer would be -11 pi over 6. Well, let's confirm this on Desmos. If I go back over here to negative, I get negative 11 pi over 6. And notice this is the solution on the left. That's the one associated with this one, and this one, etc. All the points on the right-hand side of these humps are associated with one another. Negative to 5 pi over 6 to 17, etc. So the unit circle tells me then that for a trig equation, there are always going to be two solutions for x in between 0 and 2 pi, right? One go around of the circle, there's always going to be two different places that share a coordinate. But if I want to go through and find all of the solutions, every possible angle that works, if I do not want to be stuck to just one revolution, notice that I'm still taking those two initial answers that we found, and then I'm adding 2 pi k to them. This represents every possible answer to my original function, my original problem, this equation here. Okay, so this is how we're going to go through and solve trig equations. It's all based off of this. So let's take a look at two examples. So example 1. What if instead of having sine, we had cosine? So solve cosine x is equal to 1/2. And I'm going to use both methods. Let's start by finding all solutions that are just on the unit circle. In other words, I'm just looking at the angles from 0 to 2 pi. And I'm specifically looking for where is the x coordinate 1/2. Well, looking at the unit circle, this is going to occur at x is equal to pi over 3 and 5 pi over 3. This happens in quadrant 1 and quadrant 4, which makes sense because I'm looking for where cosine is equal to a positive 1/2, and that only occurs in these two quadrants. So recognizing the sign of what we're solving for, in particular the unit circle, will help me narrow it down much faster than having to literally scan through an entire circle. I can instantly say that the answers are in between the first and fourth quadrants. And this is also an important fact when it comes to thinking about cosine representing an x value, because if I go to a circle, and this is just going to be a really quick circle, notice that I'm essentially saying for cosine, where is x 1/2? Well, this is the vertical line at 1/2, which means whatever my solutions are always going to be directly above one another. And this doesn't matter whether you're saying cosine is negative or cosine is positive. It's essentially scanning through vertically versus sine is scanning through horizontally as we go through and we set each thing equal to whatever. And so I have cosine x is equal to 1/2. We actually have those two solutions. I'll circle them in red. We have x is equal to pi over 3, and then x is equal to 5 pi over 3. But what if I want to find the expressions that represents all solutions? This means that I'm essentially looking at its graph. Well, we talked about beforehand that because sine and cosine have periods of 2 pi, if pi over 3 works, that means its coterminal of adding 2 pi works, which means adding another 2 pi would work, and then another 2 pi, and then another 2 pi, essentially any multiple that you want. Well, this is also true for if x is 5 pi over 3. Every coterminal angle would work. Here are my solutions for all possible answers. K is an integer. All right, let's look at example 2. To solve sine of x is equal to 2. All right, well, again, from the unit circle, I am looking for where is there a y coordinate of 2. Well, this should cause some problems. Do you have a y coordinate of 2 on the unit circle? I mean, you at least don't have a y coordinate for any of the special angles. So does that mean that it's a non-special angle? Well, the answer to this is actually no solution. Why? Well, go back and think about the unit circle. If sine is the y-coordinate, there is a ceiling to what sine can be, because there is a ceiling to the value of y on the circle. What's the highest point that the circle reaches in terms of a y-coordinate? And look at where we're at. So in other words, sine can never be greater than 1. And we know that because its range stops at 1. All of the outcomes for sine has to be in between -1 and 1. Meaning that if you have an equation where sine of x is equal to something greater than 1 or less than -1, there is always no solution. Always. All right, we'll take a look at example 3. Solve each of the following equations over the given domains. So here I'm going to be asking either to solve for all x, meaning that I want to see that second method, so adding 2 pi k to it. If you see 4x is in between 0 and 2 pi, that just means on one go around in the unit circle, what kind of solutions do we have? All right, so in A, cosine of x is equal to -√2/2 for all x. All right, well, I want to find an expression that represents all possible answers, but this starts by looking at the circle and finding my initial x values. So on the circle, cosine is going to be -√2/2 at 2 different places. I see that cosine is negative, so this is going to happen in quadrants 2 and quadrants 3, and will be associated with the angles of 3 pi over 4 and 5 pi over 4. But because I want my answer for all x, then I'm going to add 2 pi k to this, because this expression now represents every possible coterminal angle with 3 pi over 4 and 5 pi over 4. K is an integer. B, tangent of x is equal to -1. Notice this time though, I'm only looking for the answers between 0 and 2 pi. Now this one gets a little bit trickier because unlike sine and cosine, when I can just look at the direct coordinate, tangent is all about a setup of a ratio or the quantity between the y-coordinate divided by my x-coordinate. So ask yourself, if you were to do a y-coordinate divided by an x-coordinate, what must be true about those if I'm going to get 1 or -1 as a solution? The only way to get 1 as an answer is if x and y are the exact same coordinate. So I'm looking at my unit circle and I'm looking for where my x and y coordinate are the same, except the signs may be different. Well, that's going to happen at every over 4. So this means the answer to this, my answers have to be over 4. And this is where the negative is going to come in. Tangent is negative in quadrants 2 and quadrant 4. So this means I'm looking for my angles over 4 that exist in those 2 quadrants. In quadrant 2, this happens at 3 pi over 4. And in quadrant 4, this happens at 7 pi over 4. And these are my 2 solutions in one cycle of the unit circle. All right, well, what about C? So C is cosecant of x plus 1 is equal to 0. Now, in all of these examples so far that we've looked at, notice that all of my trig have been isolated. You're treating your trig function essentially like one big variable. And when we're solving for variables, the goal is to always get it by itself. So even here in a trig problem like this one, I want to get cosecant by itself by subtracting the 1 over. So I get cosecant x is equal to -1. Now, solving something like this is a problem that we have not really seen a lot lately. I've had you evaluate trig ratios like cosecant and secant by going through and flipping your answer in sine and cosine and tangent respectively. So that means if I'm looking for cosecant of x is equal to -1, what I'm really trying to solve here is where is sine equal to 1 over -1? In other words, where is it equal to its reciprocal, the flip? You're always going to rewrite cosecant, secant, and cotangent in terms of the big 3. This means whatever your equation has them set equal to, you're going to flip them and change to the appropriate trig function. So here, it's kind of trivial because -1 when flipped is just -1. But you'll see in part E, a problem that's going to be a little bit different. So here, to solve the original problem, I'm really looking for where is sine equal to -1. And this only happens in one place because it's a very unique and special angle. I'm looking for the y-coordinate. This only happens at x is equal to 3 pi over 2. That is the only angle where sine is going to be -1. So if you have pi over 2, pi, 3 pi over 2, or 2 pi, or any coterminal angles to that, those are the only unique places where sine and cosine can be either 1 or -1 or 0. So when your equation is set equal to something like that, there can only be one spot for that. Versus any other angles, there are always two locations where this can happen because of the symmetry of the circle. All right, D. 2 sine x minus root 3 is equal to 0, and I'm solving this for all x. So I can't just stop at one go around of the circle. I'm going to need to go through and add 2 pi k to this. All right, so I need to isolate my trig. So that means I'm going to add the root 3 over and then divide by 2. So I get sine of x is equal to root 3 divided by 2. So I'm looking on the unit circle and I'm looking for angles where sine has where my angle has a y coordinate of root 3 over 2. This happens in two locations. This happens in the first quadrant at specifically pi over 3, and it happens in the second quadrant at 2 pi over 3. Again, notice that these angles are perfectly horizontal from one another. Well, I want all possible solutions, so that means I'm going to go through and add 2 pi k to both of these. And now this accounts for every single coterminal with pi over 3 and 2 pi over 3 respectively. Here is my general expression and my general solutions to the original problem in D. All right, E. So I'm looking to solve this equation. Secant x is equal to 2, and I want to solve this for x's in between 0 and 2 pi. So I'm looking specifically in one go around of the circle, where would secant be equal to 2? But I'm not really going to be solving the secant problem. What I'm really looking for is where is cosine equal to the reciprocal of 2, or 1/2. So now I'm really solving this problem. So I'm looking at the x coordinates on the unit circle. X is going to be equal to 1/2 in two different places. This occurs in the first quadrant, specifically at pi over 3, and the fourth quadrant at 5 pi over 3. Because I'm only doing one go around of the circle, I don't need to add 2 pi k to this. Those are my final answers. All right, example 4. This is where the problem's going to get a little bit more technical. Algebraically solve each of the following equations for all x. Verify your solutions with the graphing calculator. We're going to use Desmos. I'm not going to go through in this video and check these answers. You should be able to go through and check them on your own. But I will go through and work A, B, C, and D. Feel free to skip if you want to look at different problems. And feel free again to pause at each example so you can try and attempt each one. All right, so solutions. Let's take a look at A. I have 4 sine squared x minus 3 is equal to 0. All right, like I said before, and I'm going to swap over to a black coloring, if that's okay. I really don't like looking at the blue today. All right, like I said before, I'm going to treat sine and my trig as one big variable. So I want to get this variable by itself. So that means I'm going to add this minus 3, and then I'm going to divide by 4. So I get sine squared of x is equal to 3/4. Now this sine squared of x, what this is saying right here is that I really have sine of x squared, the entire thing. Essentially there are two copies here, sine x, that are being multiplied together. Now I'm solving for sine. So much like in a problem where you would have x squared is equal to 4, or say x squared is equal to 5, I would apply the opposite of squaring, which would be a square root. I'm going to do the same thing here. I'm now going to take the square root of both sides. So on the left-hand side, I just get sine of x. On the right-hand side, I would get root 3 over 2. Can't take the square root of 3, so that stays on the inside of the square root, but I can take the square root of 4. That answer is 2. Now, we've talked about in class between mod 4 and into this mod 5 that when I introduce a square root to a problem, there are always two different types of answers. Again, just recall, when I have x squared is equal to 4, there are two numbers when multiplied together with themselves that will give you 4. One of those values is 2, the other is negative 2. In other words, there is always a plus and minus when you introduce a square root to a problem. So here, I have not only where is sine equal to positive root 3 over 2, but I'm also looking for where is sine equal to a negative root 3 over 2. All right, so this is going to occur in essentially all places where y has a coordinate of root 3 over 2. And this is going to happen at pi over 3. This is going to happen at 2 pi over 3, 4 pi over 3, and 5 pi over 3. Now, these are all the angles on one circle, where sine is going to be positive root 3 over 2 or negative root 3 over 2. But looking back at the question asked me to solve for all possible x. So this means for each one of these, I need to go through and add 2 pi k, because that is the period for sine. And it means that all of these answers will continue to replicate themselves or repeat every 2 pi. So here's the answer for A. B. All right, now in B, I have sine of x times cosine of x is equal to 0. In other words, I have the product of two different trig functions. Generally, we only have one, and I'm going to go through and isolate that single variable, single trig. But here I can't because there are two different ones. So doing what we've done before, I can't just isolate by adding and subtracting and dividing. This is where you're going to have to remember the zero product property, which says if you have two things that are multiplied together and the product is equal to 0, this means that either A is 0 or B is 0, because that is the only way to get 0 as a product. So here, if I have sine of x times cosine of x is equal to 0, this means that either sine x is equal to 0 or cosine x is equal to 0. And this is how we set up and get the equations that we need to solve. So factoring is going to come back in spades here. As we continue working through this mod, we'll get to more complex equations that we have to solve, and factoring will play an even higher role in that. So just kind of prepare yourself. It's going to kind of suck. So here, sine of x is equal to 0. I'm looking for where do I have a y coordinate of 0. This happens at 0 and pi. Now, I'm not going to write 2 pi because 2 pi is coterminal with 0. So if I go through and I write these out, this would be plus 2 pi k. This would be plus 2 pi k. For cosine of x is equal to 0, this happens at every pi over 2 and every 3 pi over 2. So I can go through and add 2 pi k and add 2 pi k. Now, one way that we could rewrite these, again, and kind of taking this one step further, and this is semi-advanced, is that notice we're essentially counting every 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. We're just counting all the pi's. So another way that I could actually express these first solutions is by just saying k times pi. Over here, this is going from pi over 2 to 3 pi over 2 to 5 pi over 2 to 7 pi over 2, etc. over and over and over and over. So I could just start it at pi over 2 and add a single pi and multiples of pi to continue, because this would be going 180, then another 180, etc. This is just two other ways to represent all the possible solutions. The initial 4 that I wrote are good enough. All right, let's take a look at C. So C is cosine of x plus 1 divided by sine of x. So cosine of x plus 1 divided by sine of x. And this again is all equal to 0. Or when I have a product and I set both pieces equal to 0, if I have a quotient, the only way that a quotient can be 0 is if the numerator itself is 0. The denominator can never be 0 because I'm never allowed to divide by that. So any of the solutions that I find, I have to make sure that this does not occur. And it means that I only really have to worry about is the numerator. So I have cosine of x plus 1. I subtract the 1 over. And I know cosine of x is equal to negative 1. This only occurs at pi, and every point from that is coterminal, so plus 2 pi k. Now, this is kind of ridiculous then, because notice at every pi, what's true? Well, at every single pi, sine is equal to 0. So that means these can't be solutions, which means there's no solution to this. Anything that would zero out that numerator puts a 0 on the bottom, which means there can't be an answer to this problem. It's indeterminate. D. Tangent x times 2 cosine of x plus 1. Actually, you know what I'm going to do? I'm going to add a page here, because I don't want you to see really the next example, which is changing the frequency yet. Okay. All right, so we've got D, which is tangent x times 2 cosine of x plus 1 is equal to 0. I think it was plus 1, right? Let's take a look. Yep. All right. So if I'm solving this, notice how this is very similar to B, where I have A times B is equal to 0. So zero product property tells me to take tangent and set e to equal to 0 and solve that. And then to set 2 cosine of x plus 1 equal to 0 and solve that. Any x's that I get would be solutions to the original problem. So let's start with tangent x is equal to 0. Now again, tangent, remember, is y over x. So I'm looking for, when I set up the x and y coordinates, where would I get 0 as a solution for this? Well, this can only occur where y is 0 and x can't be 0. So something like 1 or negative 1. Well, this occurs specifically on the x-axis. So that means x is equal to 0, pi, 2 pi, 3 pi, etc. In other words, we have the same setup from earlier, where this is happening at every pi. So I can represent this by pi k, or I think I even wrote k times pi earlier. So multiples of pi like this, where k is an integer. All right, now for 2 cosine of x plus 1, I'm going to isolate my cosine. So I would subtract the 1 over and then divide by 2. So I'm really trying to solve the question, where is cosine equal to negative 1/2? Well, this occurs at specifically negative 1/2, so that would be 4 pi over 3. And what else? That's not even the first one. 2 pi over 3. And because I want all possible solutions, I need to add multiples of 2 pi to this, because that is its period. All right, so A, B, C, and D kind of show you some more complex equations. You need to be able to solve the more basic ones, and then some of these if you want to earn up to 4 points and show total mastery. Now, outside of this, the question kind of arises is, what happens though if the period is not 2 pi? Because we saw in our models, we saw with the temperatures and we saw with the word problems, etc., that the period for sine and cosine can be changed. I can change the frequency of the wave, which means if I'm changing the frequency, I'm changing the period, and then I would not necessarily be adding 2 pi to each of my solutions. We would be getting more answers in the terms of going around the circle once, which means my general solutions would change. And so that's the investigation in the final part of this video that I want to look at. I want to look at a situation where the frequency is no longer just 1. What if the frequency was, say, 3? Well, for this, I want to find all solutions, though, specifically in between 0 and 2 pi. because if I wanted to find everything, it would be a ton of work. So for the scope of the class right now, we're only going to focus in the general circle of 0 to 2 pi. But unlike before, where we only had 2 answers, here there's going to be more than that. The number of answers depends on my frequency. All right, so I have sine of 3x is equal to 1/2. Well, let's start by using method 2, which said, well, let's just go to Desmos and let's graph. So I'm going to graph y is equal to sine of 3x, and then I'm going to graph y is equal to 1/2, and let's see how many times that these intersect. All right, so I'm going to go to Desmos. This was the original. Now again, I'm changing my frequency. So notice it's essentially like a spring. I'm compressing it, meaning that within one cycle of 2 pi, which you'll see on the right-hand side of the screen, and starting at 0 on the left-hand side of the screen, look at the number of intersections that we have. I have 1, 2, 3, 4, 5, 6. 6 total answers. Now I am not including this one because it occurs after 2 pi. And if you remember, my restriction was from 0 to 2 pi only. So I need a way and a method to find these 6 solutions without having to go through and always look at a graph and trying to figure that out. So if you notice, the first 2 answers here are pi over 18 and 5 pi over 18. The next 2 solutions are 13 pi over 18 and 17 pi over 18. And then we could continue and hopefully essentially looking for a pattern. We can notice that in terms of all of the ones that occur on the left-hand side, I'm always adding 12 pi over 18. In terms of the angles on the right-hand side, notice I'm also adding 12 pi over 18. Well, let's go to the equation and let's do some work by hand. All right, so just to kind of write this out again from the graph, we noticed that all of the answers were cycling at 12 pi over 18, which is 2 pi over 3. So let's hold on to that for a second. All right, now I want to go through and try to attempt to show you how to do this by hand. Now the first thing I'm going to do is essentially simplify the problem by rewriting it as sine theta is equal to 1/2. In other words, I'm essentially saying, don't worry about the 3x. Imagine that 3x as just one single angle, theta. And I'm going to solve this like we've done in the previous examples and in this lesson so far, where I'm going to go through and still say, where is sine going to be equal to 1/2? And I'm going to set theta equal to that because that's what my angle needs to be. Well, we know from the very first example that theta is going to be, or sine will be 1/2, specifically at pi over 6 and 5 pi over 6. So here are my 2 initial solutions. But we're not solving for theta. We're solving for x. So at this stage, I want to go through and put in 3x. Now, if we go through and we solve for x, I get x is equal to pi over 18, and I get x is equal to 5 pi over 18. And if we go back to our graph, these are the first 2 answers and the first 2 intersections that we found. Get these off the screen. Pi over 18 and 5 pi over 18. But how do we find the remaining ones? Well, if you think back again, we added 2 pi k because 2 pi represented the period for my function. But if I'm changing the frequency and I'm affecting the period, recall that the period is always 2 pi divided by my frequency. So in this case, my b is 3. So if I'm going to go through and find every possible solution, that means I'm adding with pi over 18 2 pi over 3. Well, I'm adding multiples of that. It means that if my initial solution is 5 pi over 18, the next one is 1 period away, and multiples of that if I want to go any further. Well, what I like to show people is then, if this is my expression for all possible answers, we can actually get this by when I write this step here, I go through and write 2 pi k, which represents all possible solutions that would work for theta. So that when I go through and I replace theta with 3x, and then I solve for x by dividing, I'm not only dividing by that angle, by my original answer by 3, but I'm also dividing by this, dividing this plus 2 pi k by 3. And if you see, there's that period. We don't have to go through and try to solve for it. So when we have a frequency change, you solve the problem like normal, adding 2 pi k and everything. But once you go through, we need to solve for x, make sure you're dividing both pieces by that. So then I have my general expressions here. Now I need to find all possible answers from 0 to 2 pi. And if you remember, there were 6 total answers. So I need to find these 6 total answers by hand and show you how that works. Now we have our general equation here. I'm going to go through and essentially just make a table. Well, when k is equal to 0, this gives me my initial pi over 18 and 5 pi over 18. To find the next set of answers, the next pair, I need k to be equal to 1, which tells me I want to go through and do pi over 18 plus 2 pi over 3. Well, I need to find a common denominator, so I'm going to multiply top and bottom by 6. So when I add 2 pi over 3, I am really adding 12 pi over 18, which is that fraction that we saw from the graph. This is how we can find it algebraically. So I'm going to go through and I'm going to add 12 pi over 18 to pi over 18. So that'll give me 13 pi over 18. And then I'm going to add 12 pi over 18 to 5 pi over 18 to get 17. Well, this is still less than 2 pi, so that means I need to add again. So I'm going to add another 12 pi over 18. I get 25 pi over 18. I'm going to add another 12 pi over 18, so I get 29. Well, this is still less than 2 pi, so I'm going to go again. By adding 12 pi, I get 37. By adding another 12 pi, I get 41. But honestly, I could have stopped here. And the reason why is look at the numerator. It is over twice the denominator. In other words, 2 pi in terms of 18ths is equal to 36. So I know that if I double the denominator, once my numerator is higher than that, I am done. Here are all possible answers, and notice there are 6 of them. Essentially, the idea stems from the frequency, right? If normally there are 2 answers to every basic unit circle problem, if I make the frequency 3, I am tripling the amount of solutions, thus 2 times 3 or 6. So if I was to rewrite the problem and say I had a frequency of, say, 5, that means there would now be 10 solutions from 0 to 2 pi. All right, well, as you saw when I was scrolling, I've got one final example for you to go through, and we'll practice doing this for where the period or the frequency has been altered. So solve each equation for x in between 0 and 2 pi. All right, starting with 2 cosine of 3x minus root 2 is equal to 0. All right, well, so I'm going to go down to the below this solution. And I'm going to take out the 3x and just put a theta in to make my life a little bit easier. It's equal to 0. And so I'm going to solve this like I would normally. Cosine of theta, I'm going to add the root 2 over, and then I'm going to divide by 2. And then I'm going to ask myself, all right, well, where is cosine theta? Where is cosine specifically equal to root 2 over 2? Well, this occurs on the unit circle at pi over 4, and it occurs at 5 pi over 4. Whoops, sorry, 7 pi over 4. But not only that, it occurs at every 2 pi after that. But I'm not solving for theta, I'm solving for x. So I'm going to put 3x back in for theta, bringing down the right-hand side to both of these. And then I'm going to go through and now solve for x by dividing by 3. So I get pi over 12 plus 2 pi over 3k, and I get 7 pi over 12 plus 2 pi over 3k. Now the 2 pi over 3 we saw in the last problem because it's the same frequency. And so now I can go through and find my 6 solutions. by taking my original, pi over 12, and 7 pi over 12, and I'm going to add 2 pi over 3, or 4 pi over 12 to each of these. So starting at pi over 12, the next answer would be 5 pi over 12. For 7, this would be 11, then 9, and 15, 13, 19, 17, 23. Notice 23, I'm stopping there because I don't need it anymore. If I added 4 to 17, actually this is still good. I can go again. So this is actually 21 pi over 12. And then this would be 27. So at that point, it's too much. That one's no more. Here are all my solutions. Notice this one actually has way more than 6, which is kind of interesting. Let's go to the graph and check it. Maybe I made a mistake. Okay, so we're looking for where is cosine. Let's see, functions, cosine, 3x. And I'm setting this equal to square root of 2 divided by 2. We'll do y is equal to. So we've got 1, 2, 3, 4, 5, 6. So I definitely made a mistake somewhere. So what did I do wrong? So let's go through and look. You probably already found it, and I just haven't yet. All right, so we got pi over 12. Well, that was the first answer that we got earlier. And then I have 7 pi over 12. So we got that. If I add 4 pi over 12, I get 5 pi over 12. And that's probably my mistake. Oh, because I'm not supposed to be adding 4. What is this part right here? It's supposed to be 8. You probably already saw that. The over 12 part's right, but it should be adding 8 each time. So that means when I added 8 here, that should be 9. When I add 8, this term is gone. That should be 15. When I add 8 to 9, I should get 17. Add 8 to 15, I should get 23. Now I know I'm done. And there are my 6 solutions. So notice that that rule that I said earlier, where you normally have 2 answers and we can multiply it by whatever my frequency is, in this case 3, I should get 6. So when I started getting 8, I should have instantly known that something was wrong. And that's what was wrong. I had screwed up on my period when I was trying to go through and simplify. Okay, so here are my 6 answers from 0 to 2 pi. All right, that was A. All right, let's look at B, and then I'll leave C as an example for you to try and go through and do. So I know this video is getting long. All right, so I'm going to solve. So tangent of 2x here, I'll go down. So I got root 3 tangent x. I'm getting lazy. Tangent of 2x is equal to 1, negative 1, 1. All right, again, I'm going to replace 2x with just a single theta, and I'm going to isolate my tangent. So I'm going to divide by root 3. And now I'm looking for, when I do my y over x, where would I get essentially a radical 3 in the denominator? Or where would I get a radical 3 in my x coordinate? Well, this means that the original values were 1/2 and radical 3 over 2. The over 2's have canceled themselves out. In other words, tangent's going to be a positive 1 over root 3 when theta is pi over 6, and when theta is 7 pi over 6. Now, tangent specifically is actually really, really interesting because tangent, remember, cycles every pi. And if you notice, if I'm starting at pi over 6, the next solution would add a pi to it. well, that would give me 7 pi over 6. If I add another pi, I would get back to this next coterminal, and then et cetera, et cetera, et cetera. So we'll leave this, and let's just kind of double check and see if it matters, if we need to list both, and we'll go from there. So I'm going to replace theta with my 2x. So I get pi over 6 plus pi k. 2x is equal to 7 pi over 6 plus pi k. I'm going to divide by 2, so I get x is pi over 12 plus pi over 2k. And here I get x is equal to 7 pi over 12 plus pi over 2k. All right, and if you notice, if I go and I start listing out my answers, pi over 12 would be my first solution for k is equal to 0. And if I was to do k is equal to 1 for this first one, I would get plus pi over 2 or 6 over 12, which is 7 pi over 12. So we're getting this answer out of it. And this is what I was trying to say earlier, where these two answers are actually the same and involve the same values. So I really, for tangent, I only have to go through and solve this one on the left. And it's because of its period. We just need to find that first quadrant for tangent. So I'm going to keep listing out. So k is equal to 2, and add another 6 pi over 12, which give me 13. I go one more time. I would get 19. And I know I would stop here because the next one would be worth 25, which would be too much. So I'll only get 4 answers here because we're only getting one solution total for tangent. So 2 would make 4 overall. But this is it. All right, and that's the solution to part B. So I'll leave C as an example for you to kind of work through. And then if you want to see any work done, I would encourage you to join my virtual class check-in. So maybe that'll spice that up a little bit more to get you to come to those. And then if you have any other questions with solving these equations, let me know. A natural question that comes up from this would be, we could solve all these because my sines and cosines were always equal to something on the circle. So like 1 over root 3 and 1/2. But what if I wanted to do something like, where is sine equal to 0.8, something that could exist on the circle, right? 0.8 is less than 1. So there's an angle associated here, but it's not associated with a special angle. So how do I solve this? We'll do this in the next video. All right, so that's it for this video. Take a look at the practice problems, and then as always, let me know if you have any questions.